Well, everyone, thank you for being here. My name is Ryan. Most all of you probably know me because I'm here almost every week doing the computer club. Today, we're going to talk about procedural generation, and specifically, I'm looking into making art and worlds and doing interesting things, trying to simulate real life a little bit with basic, simple algorithms. Not that they're basic and simple to implement, but their ideas are super basic and they rely on just a couple of interesting principles. So I have 5 demos prepared. We're going to go through all 5 of them. They're based on 5 demos, but 4 different, completely kind of unique concepts that are all kind of useful and viable for doing art worlds, but also more useful things. There's applications here in signal processing and simulation and all kinds of other stuff. So, and this is by no means like a comprehensive list of generation techniques. I'll talk about some more at the very end if there's time, but these are 5 of my picked out ones that I think I could implement, and I did in just a couple of days. So, obviously, what is it? We're basically wanting to create complex data and be able to replicate patterns and make new things across infinity if possible, using only kind of a compact rule set. You can imagine for games this is useful if you want to have an open world like Minecraft. It's near impossible to, you can never hard code every block in Minecraft and where it's supposed to go. Instead, you've got to come up with some other way to place all of those things and kind of make it make sense and look natural. And so the challenge, obviously, and I included some images here, is that simulating nature is not random. Nature is actually very ordered, and especially as you look closer and closer, this is a cool example of a leaf, which is I don't know that it's exactly a fractal, but you see lots of patterns like that in nature. And so this is all to say that pure randomness is not going to cut it for all these things. If we could just shuffle everything and it would look normal, that would be awesome and it would be super computationally easy, but that is not the case. We have to come up with something a little bit more complex most of the time. And so now the way that we do that is changing all the time, and there are lots of them. But just for a quick little history, some of the first of procedural generation stuff was for old video games. This is Maze Craze for the Atari, original Atari, and it had a system in it where it would generate you new mazes every time. And of course, it's an Atari. It had kilobytes of memory, most likely, maybe megabytes. So obviously they couldn't hard code a ton of mazes, so they had to come up with something clever. And this is one of the earliest examples of procedural generation and kind of this idea of infinite worlds that are all sensible and follow rules and make sense and they're easy to work with. And then on the right there, I have a picture of the thumbnail of No Man's Sky. If anyone's familiar with that, it's kind of like a kind of poster child of procedural generation techniques. They claim to have a effectively infinite universe of all procedurally generated planets that you can explore, and they're all super rich and full of life. And I haven't played in years, but used to be able to take everything apart and get materials and I don't know, are there animals now? Yeah. There's animals, so it's super interesting. Um, and we've come a really long way, and this is all kind of relying on this basic kind of math and processes that I'm going to show you guys today. And so here are the 4 algorithms we're going to talk about. The first one is Perlin noise. You've probably seen or heard of this before. Basically, this allows us to get a noise function, and noise is just kind of random numbers across a plane or even a single line. But Perlin noise was kind of a first attempt at making that smooth. And so I'm going to show everyone a picture when we actually get to it, but it's going to look kind of we can easily represent it with pixels on a screen, but somewhere in between white and black for numbers in a range. And so we can kind of commonly represent it as that, and it'll be like a bitmap image, and you'll be able to see kind of gradients between white and black across it, and they'll be smooth enough. And so that's important because when we try to simulate nature and terrain, and even do some of the art I'm going to show you guys, uh, most of the world functions this way. It's kind of smooth gradients that are random enough in themselves, but overall form some kind of order. And now one note about Perlin noise is it's not the standard anymore. It's still used because it has some cool properties we like, but OpenSimplex and OpenSimplex 2, please consult Armin. He's kind of a pro at those two, but those are the new standard for computationally efficient and good. There's also the question of when you're trying to implement this in a huge game like Minecraft, can I walk a trillion blocks to the west and then plug numbers in and still have them make sense and look good and not take a million years to compute? Because this needs to be fast, needs to kind of run all the time deterministically. So the next one then, you might be familiar with Conway's Game of Life. You maybe have played with it. It's like that little grid of cells, and you can place them, and there are rules for them. Like if two cells are next to each other, they'll create a third. But if there's three or four, then they'll delete one. And you can kind of get like these weird emergent structures to come out, and they'll like build things and move across the screen and follow interesting rules. We have a little simulation in our demo today that uses a cellular automation to follow rules and try to simulate something. But this is kind of a famous example, and I think it is really cool and shows some of the emergent properties of just like simple rule sets and see what happens. Next, we have Markov rules, named for Andrei Markov, I think, but an ancient mathematician, and by ancient I mean like the 19th century, maybe the 20th. But what these are, if you're taking 341 right now or CS 280, you'll hear about grammar rules. And so one of the implementations we'll look at today is you take these terminal and non-terminal symbols. I don't like saying it either, and I hate to admit, but it's kind of cool and useful. And you can use those to make rules and continue to generate patterns that follow grammar rules in procedurally generated worlds. And then finally, and this is like a cool, like really hyped up one, but the wave function collapse. This is like, there's an interpretation of this in quantum physics with the way that like, everything is equally probable until we collapse onto the actual solution. I'm going to talk about it at the end of the presentation, but it is a cool one, and you'll see people doing like really interesting, complex stuff. If you've ever heard of the game Townscaper, I have some screenshots from it later in the presentation. That's a really cool one that uses the WFC to generate like a super cool little world that makes a lot of sense. So here is the first one we're going to get into, the flow art. So this is based on a guy named Tyler Hobbs who does this art. He's linked in the bottom of the page. But what he does is he's making these like screens that are like just full of lines. They're all like point in cool directions. And now in the demo that I put up, and you guys are welcome to follow along with it, we can like play with all the parameters and watch it animate and do different things. And you'll see that these are all kind of, they're interesting and unique. And I think they're kind of pretty. I don't know about you guys. I got different colors too. Tyler Hobbs does a really nice job, but I think this is a super cool one. The way that this is working, and this is what I'm talking about earlier with the Perlin noise, you can see how it's kind of like smooth in between spots. It's not like that first noise I showed you guys that was like random pixels. This is smooth. You can see like kind of definite shapes and structure, and like you can tell that somewhere in here it's sort of sinusoidal a little bit. Y'all see that? Kind of. All right. So this is just sampling the pixel color based on the algorithm. What I do is I plug in an X and Y coordinate, and there's a 2D, there's a 3D, there's a 1D. So this is 2D. I plug in X and Y. For 0, 0, I get this color. And for any point that I sample along it, it should get like kind of a smooth gradient in between. And now this is obviously black and white, but we can also interpret those things as vector fields, which is kind of interesting. Instead of saying, all right, this is like RGB whatever, I'm just going to say this maps to, some angle. That's cool. And that will nicely show we get these smooth like vector fields. And so you can see how this kind of goes into how this art is made. If we have vectors all over here pointing in nice discrete directions, what we can do is we can pick a random one, follow it, then I'll land on a new vector, and I just keep following them. I draw these nice smooth lines. And this is, of course, with Perlin noise, but I also wanted to throw in a couple others. This is Perlin and then scaled or quantized by pi over 10. So you can see, let's see, these ones will be like a little bit more jagged, and especially as I turn it down. It's kind of like, you could just see these are like slightly different. Cool, kind of interesting. I recommend you check out Tyler Hobbs because he actually put together like a bunch of really pretty ones and did more stylizing than I did. So if you're interested in that, that's kind of how it goes. But then again, pseudocode, which you're all welcome to read in more detail, but we just sample a color from the Perlin noise like bitmap, but then we turn that into an angle between 0 and 2 pi. Then we just pick a bunch of random spots to start a curve, and that's based on those parameters I was setting. Sample it, go a couple pixels forward in that direction, and we just use the sine and cosine of the angle it's going to go at. And then we get to a new spot and just keep following it. And we draw a bunch of lines. And it just happens to follow like this really pretty structure I mean, I think it's pretty. I like that. I could sell those, right? All right, I'll try. So that's the first one. The next one, it's obligatory, was we had to do a little bit of Minecraft. This is actually really fun to play with. If you just like go on your laptop right now, you can do all this and you can drag it around and scale it, move it, do all these things. Look at that. Isn't that interesting? I like this. I could do this all day. Um, but this is cool, and it's using Perl and noise once again. Sorry, OpenSimplex, there was a JavaScript Perl and noise implementation I stole, and this is just easier. But this is a similar concept, and I encourage you all to play with it on your own time. We're actually using a fractal Brownian thing here, and all that's to say is we're doubling the frequency and having the amplitude, and then adding layers of noise where we apply that over and over again. And those are octaves, if you see in this slider, octaves here. So for every octave, I take the same Perl and noise function, I double the frequency, half the amplitude, and then just add them. And what that does is it gives these like kind of more jagged curves, but which still makes sense. I know this is a little bit low resolution. Um, but then this also just brings up the idea we can stack and layer noise in all kinds of ways. Different types of noise, noise with different parameters, noise scaled, noise cubed, noise whatever. And we can use it to kind of get these different like, sort of patterns. You can see like some of these, if you're just going to consider this in like Minecraft context, this fits with like kind of an island biome. This could be like trees. This could be, whatever. And so you stack all these things, get different stuff. Uh, Pretty effective. And then obviously we have all those parameters in here. We can double up the octaves, and you'll see it gets just a little bit more complex, a little bit more jagged. And then obviously playing with the noise scale as well, you can see same thing, getting more or less jagged. And then just as far as implementation of this, all I'm doing is I'm sampling like my total noise. If it's a 5, I go up 5 blocks and place a block and just color it. And I'm not going to go, I have a separate presentation plan for like, this is using Three.js if anyone's curious, which is just like a JavaScript rendering library, which is pretty optimized that my laptop can run this thing like really fast and it looks good. So yeah, that's basic implementation, and then all I'm doing for the colors is just based on their heights. You can see like this is clearly the threshold for snow blocks, and they just go there, and sand always goes next to water and all that stuff. And we have like a water level. So this is a pretty cool one, pretty easy. If you're curious about this specifically, all the JavaScript is very findable. If you go to this website and press Control-Shift-I or whatever your inspect button is, just steal the JavaScript files from there. I'll have them posted as well. But that's our other use of noise. And you can see similar algorithm, sample the thing, pick a thing, draw the color. All right, this one's fun to me. This is our cellular automation, automaton, and it's to simulate fire. Isn't that kind of interesting and weird? I gave a ton of parameters here because honestly, it's kind of hard to get the fire to like work quite right. Like if I crank the burn temp, it like looks kind of too bright, and I can turn wind on. Isn't that cool? I kind of like that. And you kind of kill it easily. Anyway, this is basically to show this is like Conway's Game of Life. Every cell in this grid, and I can set the resolution of the grid too. I think actually 120 actually looks really good. I think this looks awesome. So cool to me. But for every cell in the grid, we just are running this simulation where every cell has a color, and that color just corresponds to a state. So it's really simple enough. I'm just gonna keep this guy going. He's so cool. Burn. I don't actually know how to make it longer. Yeah, every cell in the grid has a color which corresponds directly to a state. Obviously, there's on fire. Obviously, there's smoke. Obviously, there's wood. But then they each also have like a value, which is the burn temperature. And so the actual like math that goes on here, and here's some Noita stuff, but yeah, I don't even know if I wrote it out, but there's an ignition temperature of the wood, and if the nearby corresponding like fire or any block is a fire with temperature higher than the ignition temperature, it has a chance to spread. And it's a chance to spread. It doesn't always, and I can adjust that as well. And so then there's also the heat decay. If it gets further away from the fuel, it will start to like tick on its life. And then smoke as well has a state, which is basically a value of how many more cycles it has left before it's gone. And so kind of cool with like, 3 basic rules pretty much. we're kind of simulating like this really cool thing. It's fire. And then the wind, obviously, like it's pretty basic. But you can see how doing something like this, you could also simulate more interesting things. This is useful for stuff like water simulation. There's a lot of physics demos that use stuff like this. Like below, I showed you guys Noita just a little while ago. But it's a world where like every pixel is interactable. So you could shoot this with a gun and they'll literally start burning and then like start following their own rules. This thing is doing whatever, this thing is acid, it might eat through blocks. But you get like these really cool emergent worlds out of like allowing all the particles, I guess, to interact with each other. I think Noita actually got nominated. I don't know if they won, but for like most creative game or like use of environment or something back when it came out. It's a really cool game. And over here, I obviously linked Claudio Conti, but these are like cellular automata art, which I don't know, like some of these are kind of crazy and trippy and weird. They're kind of like our line art and stuff that we were doing earlier, but using cells with simple rules, and we get these cool patterns out. There's also, if you guys like are really interested in this, there is like I think there's a YouTube channel called Emergent Garden, and I watched him do a video where he gave like a bunch of new rules to cellular automata. I think it was like a video actually about vibe coding anyway. But he was implementing these things and managed to get like a ton of really interesting shapes and stuff out of here. If anyone's interested in that, find me after and I'll get you the video. But this is like you could do really cool stuff with simple rules, is basically what this is looking to say. And I like these arts. I would hang up some of these in my house. Like I don't even know what this guy is, but I think he's super awesome. And yeah, so here's the rules. Every tick, we check all the cells with fuel. If the heat is greater than the ignition, then we start burning and we start subtracting fuel. When we run out of fuel, we turn into smoke. Otherwise, we try to spread. And then at the end, we apply all the wind. We can deteriorate everyone and like do some post-processing just for the graphics. All right, cool. Now, this one is kind of fun. My friend said I should post this on Twitter because it would go viral, but I really don't think so. But I think it is cool. This is a room generator. Every single time you press the button, you're going to get a new room. And they're slightly different. They always make sense enough. Don't mind these gaps. It's because I reused like these assets that aren't mine. Sorry. But every time you do this, you're going to get something different. You can also play with this and make the room bigger. I really like it. I think it's cool. The speed makes it do like more fast or more slow. If it's working, I don't even know. Yeah, it's working. It's working. So anyway, this is kind of cool. This is replacement rules. Everybody loves it. And this is actually stolen right from the circuit board. But what we can do is treat replacement rules instead of using like terminal and non-terminal symbols. We just map those symbols to pixels on the screen. And so what I'm doing up here is I'm saying like, one of the rules is like we place the walls. The next rule is we place the paintings. And so the painting rule is if I have a background wall next to a background wall and neither of them are a lamp or a furnace or whatever, place a window. And I'll just do that. I don't have to have like a terminal symbol. I just say run the rule 5 times and I get 5 paintings. And the same thing goes for all the other ones. The rule for chairs, for example, is like, if I'm on the floor in an empty cell, or I guess they actually write over the cabinets, but don't mind that. If I'm on the floor looking for, if I have this cell below me and this cell is me, then I can replace with this cell in a chair. It's kind of cool. You guys remember the PDAs? It kind of feels like that to me. I'm sorry. Yeah, but super interesting one. And I was showing everyone before the presentation. Come back. This example comes from another guy who did like a ton. His GitHub repository is called Markov Jr., but he wrote a ton of these to generate like some really interesting stuff. I'll probably pull up the GitHub at the end. But my example is really simple, and you can generate like really awesome stuff out of this, like totally unique houses and circuit boards and art and all kinds of cool stuff. But up here you can see, now my implementation uses like a rule allocation. So like I get a rule budget for everything. So there's only one time we run the pass that like replaces the outside with walls. There's only one time we run the pass that places a bed. But there's 5 passes for placing the paintings, just because I think it looks good. So all we do is we just run the rules, we look for matches, and then we replace them. And you could also imagine like Up here, I have rules that could be recursive, like they could call themselves, and like I could have fractals inside my generated images, which would be cool, and I would like to do it someday, but maybe not today because I only just had a little time to work on this. This one is super cool. This is the wave function collapse, and its interpretation in quantum physics, which I may disagree with or not. I think it's correlated, but not exactly. How this works is I have a bunch of unique like elements. An element is like a single piece. It's this corner piece and this one, and a straight road, and like a fork, or this house, or the factory down there, the car. They're all individual pieces. I think there are about 21 of them total in this example. But what this does, I'm going to make it really small just for fun. Um, I'm just going to turn this really slow too. Come on. Come on. Oh, Jesus. All right, look at that. What it does is it seeds the outside and then just starts picking stuff that can kind of fit with it. These are like puzzle pieces, and they all have like compatible sides. For example, this roadblock can go with this corner, but it can also go with this corner. And this factory can have anything around it, but not the church. I don't know, that's a rule, sorry. Um, Basically, this is interesting because what we're doing is we're kind of simulating entropy. And so when we start, the grid is completely blank. There's nothing on it. Every cell, especially the ones in the middle, you could think about them having an equal probability of any cell being that cell, right? If I'm this cell before the generations run, my probability of being the factory is just as high as my probability of being the elbow piece. So all the probabilities are 1. Then we fill the outside, and then what we do is we can say, okay, this one has 2 grass blocks next to it. So now we've crossed out the possibility of this, 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 and this. And now we can go ahead and pick something else. So if we pick the corner piece, then boom, we just knock out half the options. And we keep doing that. And the reason that you guys see it like resetting over and over again is because sometimes you'll get to an impasse where like you have 4 roads coming to the same like middle intersection. There's no piece that's like across. So you get there, and in a smarter implementation, it would just backtrack recursively. I wasn't that smart, so I just said if you have like an infraction and you can't get past it, just restart. I figured that wouldn't be a problem that much of the time. Most of the time it's not, but you can see like half the time it kind of resets because it ends up at impasses where there's nothing for it to do. Like especially if I make the grid really big, I can run this thing all day long. And this is going really fast, trying to get a solution, but it probably won't, to be honest. We're better off with like ones that size. Come on. Come on. I just want to see a couple more because they're really cool. But once again, all that we have to do to set this guy up is define all our tiles, say who they're compatible with, and then let the algorithm run. And it collapses to these solutions. That's why we call it wave function collapse. And then, yeah, a little more about how this guy works. And this is a screenshot from Townscaper, which I think is like a really cool, like pleasant game. It's very cute. You can like click and these things make like an adorable noise, and the whole building like shifts and grows. I wonder if I could get some gameplay up at the end of here. But it's awesome. They use the wave function collapse, and there's some cool videos on YouTube of their dev kind of explaining how that works. One of the classic examples is these flowers here and this city skyline. If you search for wave function collapse algorithm examples, you get these two every single time. But it's also great for stuff like making mazes or these patterns or even like cool circuit boards and things. And I didn't include a picture, but yeah. And then as far as the pseudocode behind the behind our example, every cell has an option. So while there is a cell with options, and we choose the one with the fewest options. So if there's one guy and his only option is the road, is this road, we choose him, we make his decision, and then we continue through the set and just like make decisions as everybody approaches like a low entropy, and their probability of being any one thing gets much higher. And then, yeah, this is dumb. Don't do this if you're trying to make this efficient. But if any cell has no options, just reset it and try again with a new seed, of course, because we need to reset the seed. All right, and then just a couple things. Implementation notes. I use Mulberry32 for my PRNG. And then what's my it's make Perlin is the JavaScript Perlin noise implementation. Super cool people taking care of those. Shout out to the JavaScript people. I'm not usually a JavaScript person, but I had a lot of fun implementing these. Uh, got Cursor to help me a little bit, but in the end, I know how they all work, and I had fun kind of building them. If anyone has any questions or wants me to elaborate or show off some of the examples I talked about, very happy to do so. But otherwise, thank you all for your time. Happy computer clubbing. Woo, 55.